Have you ever wondered how your phone screen is so incredibly scratch resistant? Or how about a drill bit that can just chew through solid steel without getting dull? Well, the secret is all about building a perfect ultra-thin coating, literally one layer of atoms at a time. So today we're going to dive into the two incredible methods that make all this microscopic magic happen.
And really, it's not just phones and tools. I mean, think about the durable, gleaming finish on a high-end watch, or those crazy specialized reflective coatings on satellite parts. How on earth do engineers create these perfect high-performance layers? The technology, as you'll see, is as precise as it is powerful.
The answer comes down to two techniques: chemical vapor deposition, which we'll call CVD, and physical vapor deposition, or PVD. The easiest way to think about this is a chemical recipe versus a physical transfer. Two totally different paths that get you to the same place, a flawless, engineered surface. Let's start with the recipe.
So how do we get that perfect finish? It all comes down to a field called vapor deposition. You know, the core idea is actually pretty straightforward. You take a solid material, turn it into a gas or a vapor, and then you precisely deposit it back onto a surface to build a completely new high-performance layer. This is how we give everyday objects some pretty extraordinary properties. All right, first up is chemical vapor deposition. Honestly, the best way to think about CVD is like baking a cake directly onto a surface. You're not just slapping on a layer of frosting, you're using ingredients, in this case gases, to kick off a chemical reaction that creates a brand new layer right from scratch. The key here is right in the name, chemical. We're using what are called precursor gases and a heated surface. And that heat, well, it acts just like an oven. It provides the energy needed to trigger a chemical reaction that transforms these gases into a solid, durable film that's bonded right onto the object. So, how does this chemical recipe actually work? It's really a four-step process. Okay, so first, we introduce our ingredient gases into a reaction chamber. Second, we heat up the object we want to coat. In this field, they call that the substrate. Third, that heat triggers the chemical reaction right there on the surface of the substrate. And finally, that reaction creates a brand new, solid film that's perfectly bonded to the object. Simple as that. So, what's the big advantage of this chemical approach? Well, because it uses a gas, it can flow into every single nook and cranny of an object, no matter how complicated. This creates what's called a conformal coating, which is just a fancy way of saying a perfectly even, uniform layer. Plus, by just changing up the gas recipe, you can create films with all sorts of different properties, from being totally clear to being mechanically super hard. Now let's flip the coin. If CVD is like baking, then physical vapor deposition, or PVD, is way more like spray painting with individual atoms. There's no chemical reaction happening here, none at all. It's a purely physical process of moving material directly from a source right onto a target. So here's the key difference. With PVD, you take a solid material, you vaporize it inside a vacuum, and then those atoms literally travel and stick to your object. That vacuum is absolutely crucial. It clears the air of any other particles, giving the atoms a clean, straight path to the target. It basically prevents any unwanted reactions or collisions along the way.
The process is actually pretty elegant. First, you create that high vacuum. Second, you vaporize your source material, and you can do this by essentially sandblasting it with ions, which is called sputtering, or just by heating it up till it evaporates. Third, those liberated atoms fly in a straight line, and fourth, they land and condense on the substrate, building up that ultra-thin film atom by atom.
And what do you get from this direct physical process? The results are incredible. PVD films are known for being extremely dense, super pure, and having amazing adhesion to the surface. And because it's a direct, line-of-sight process, you get fantastic control over the film's thickness. This makes it perfect for creating those super hard, protective coatings like that gold-colored stuff you see on drill bits that can resist all kinds of wear and corrosion. Okay, so we've got our chemical recipe, CVD, and our atomic spray paint, PVD. Now for the big question, when do you pick one over the other? This table really sums it all up nicely. You've got the mechanism, chemical versus physical, and the key benefit, uniform coverage versus high purity. But the most critical difference, the one that's often the deciding factor, is temperature. CVD usually needs really high heat to get those chemical reactions going. PVD, on the other hand, can run at much lower temperatures. And that one thing often determines everything. So, you see, it's not really about which technique is better. It's all about choosing the right tool for the job. And that choice really comes down to the material you're working with and the shape of the part. This is the heart and soul of CVD. When you have a really complicated part with lots of nooks and crannies and internal surfaces that all need a perfectly uniform coating, the chemical recipe approach of CVD is your ideal solution. Why? Because the gas gets everywhere.
And here's the flip side. When you need a super durable, pure, and strongly bonded coating on something that would just melt or deform under high heat, we're talking plastics and polymers here, the low-temperature physical process of PVD is your go-to technique for sure.
And that's really the ultimate takeaway. The choice between CVD and PVD boils down to the shape of your object, what it's made of, especially its heat tolerance, and the exact properties you need that new surface to have.
From our phone screens all the way to spacecraft, these engineered surfaces are absolutely everywhere, making things stronger, more efficient, and sometimes even more beautiful. As we keep mastering this art of building with atoms, you have to wonder, what incredible new materials and possibilities are just around the corner? That's a question for the next generation of engineers to answer.